Why would a scientist have an interest in a shipwreck that's lying in 4,000 meters of water in the North Atlantic? The answer to that is, it's a time marker. That ship, when it sank, was brand new, and anything that happened to it or the environment in the 80 years it's had been there allows us to see what's happening over time. And when we're in the bottom of the sea, we very rarely get anything that can give us a time mark. And the Titanic was an ideal object for us to give us an idea what's happening in that deep sea environment. Quite often we see features on the seafloor such as sand ripples, sand waves, dunes. We actually have no idea how old they are. Could be 1,000 years old, could be 10,000 years old. But when the features interact with the ship and the wreckage, we know they're happening today. And that was very interesting because we're now almost in 4 kilometers of water, and we have evidence of significant current activity. In this case, we have internal waves going across the bottom of the ocean that generates these symmetric ripples, same ones you see at a beach. So the idea of using a shipwreck as a time marker, in this case, gave us control on time. One of the interesting geologic issues that came out of actually the discovery by Dr. Bob Ballard was that he was concerned the ship, being 46,000 tons, might actually sink into the ocean, the primordial oozes of the deep sea, and not be found. Then when the ship was discovered on the seafloor, then the question became, well, how can that be? It was such a huge weight, why is it resting on the seafloor? And that was a geologic question, and the research we conducted actually not only solved the problem, but it generated a whole bunch of interest in geohazards. We discovered that Titanic was only buried in the bottom by 3 to 4 meters, maybe in some cases up to 5, and that was a bit of an enigma. On research and collecting sediment samples from the seafloor, we learned that the seabed actually was a landslide scar. And of course that material is very dense and very difficult to penetrate. So it explains why the Titanic was sitting on the seafloor. Now what was even more interesting, of course, we then discovered it was at the bottom of a canyon. You can see a large canyon, and that canyon represents the scar. Well, now that had a consequence, a very practical one, because landslides, submarine landslides, like on land, are a hazard. In this case, a hazard to communications cables. They can be a hazard to deep sea pipelines. You know, the serendipity of our research in this case was that we recovered a piece of steel from the bottom to look at corrosion processes. However, the piece of steel we recovered looked like a piece of broken china. So in working with Department of National Defense, they analyzed the steel and discovered it was very brittle. This, of course, was a new knowledge. It was not known, in fact, it wasn't known until the 1930s that steel could be brittle, and that the steel went into Titanic was brittle. It wasn't substandard, it was the best they could make of the day. And so the Department of National Defense determined that because of the sulfur content of the steel, it was very brittle. The consequences are that the iceberg that went down the starboard side did not only pop rivets and deform plates, it actually cracked and fractured those crates, and that left the situation where you had massive amounts of water entering the ship very quickly and causing it to sink in much more rapidly than they thought. From a biological and geochemical perspective, some very unusual processes on the bottom. We have, in fact, rusticles. They were, in fact, discovered by Bob Ballard. They looked like icicles, except they were very rustic in color. The surprise was that the rusting and corrosion on Titanic was a biologic process. Not like the chemical process on your car. It's biologic, and it's actually bacteria that are munching away and eating the steel to derive nutrition, and their byproduct is rusticles. That process is very not understood at all. It occurs under high pressure and occurs in the deep sea, and has spawned a great deal of interest in this kind of corrosion process, especially if you want to put structures in the deep ocean. Well, we had 132 personnel on the cruise, of which 11 were scientists and technicians who were investigating the wreck itself. The exciting part, we did really prove that the ship was a good time marker and that we have a much better idea what the active processes are on the seafloor, whether they're geological, biological, or chemical. Now the exciting part of this is you have a crew like that, and we just love to get together again and 25 or 30 years later go back to the site and see after that time period how many changes and what's going on the seafloor. Do we have much more active bottom currents? Is our landslides are occurring more frequently than we expected? Has the corrosion caused part of the shipwreck to collapse, or a lot of it to collapse? So we can still learn, and now we have a benchmark from that's 25 years old, and given an opportunity, we'd all go back to the wreck, and I'm still interested in determining just what we can learn about time, and when it's a key element to geology.
If you like this video, let us know with a thumbs up. Click on the logo below to subscribe to the Simply Science channel and click the bell icon to be notified when we upload new videos.